I have recently been very interested in Euclidean spaces when equipped with a different measure than Lebesgue. Simple examples are when your measure is given, its Radon-Nikodym derivative is a weight W that is an almost everywhere positive and finite function that is also locally Lebesgue integrable so that you can integrate it to get a new measure. A notion that you can discuss for such measures is whether they satisfy a p-Poincare inequality. So some notation, first of all, p will be a constant between 1 and infinity. We will assume that measure of the balls are positive and finite. This will allow us to talk about average integral over balls of different functions. So by definition, this will be simply integrate the function over ball and then divide by measure of ball. So it's simply a shorthand to avoid writing that denominator every time. So with these technicalities out of the way, the key requirement for p-Poincare inequality is that with a uniform constant c, if you subtract the average value of the function u from b, so this is average value of u over b, if you subtract it and take absolute value and again take integral average, it will be bounded by diameter times the integral average of gradient to power p and then 1 over p root. We require that this hold for every ball, and here is the whole point of my video today, and for what class of functions. And I want to talk about some delicate matters that are tied with this choice. There are two conditions. One of them is that we shouldn't put functions for which this inequality cannot hold or does not hold. The simplest is when you have, let's say in R1, you have a function that takes two different constant values. Then the gradient for this function obviously is always 0. And the integral, the oscillation is definitely not 0 because at least one of these constants will not be equal to the average, and in that case this will be a positive quantity on a positive measure set, so this will be positive and there is no chance this inequality holds. So first of all, we cannot just blindly ask it for a huge class of functions like LP functions. And the second requirement we have is that we want let's give this star. We want star to hold for Sobolev functions because that's what is needed in lots of PD and stuff, and the original idea of why we need p-Poincare is closure in Sobolev norm, which is LP norm of u plus LP norm of gradient of u. So in this norm of C infinity omega functions, why not ask by definition for all Sobolev? Well, of course you can do that. You then put all the hard work into your definition, but then the thing is that usually before building this whole class of Sobolev spaces and all the machinery that goes with them, you don't want, or you don't know a priori if these class of functions will be nice enough to satisfy such a delicate inequality. For example, why is this average well defined, or why the derivative makes sense, or in what sense does the derivative make sense. So you cannot just hide all these technicalities in the definition. So why not ask star as part of definition to hold for Lipschitz functions. And here the bonus, the benefit, the pros is that now gradient u makes sense in classical sense by Rademacher's theorem, which has been featured many times in Young measures. Rademacher's famous theorem. And the cons is that we don't know. Again, we're assuming something here. So how do we know if Lipschitz functions, or more generally local Lipschitz functions, deserve to satisfy p-Poincare? So we want p-Poincare to hold for nice functions, for functions that are regular, that have first order derivatives. And at this point, or when you're developing a theory from scratch, you don't want to jump ahead of yourself and say, okay, I'm trying to build a Sobolev class as closure of C infinity functions, but let me go ahead and assume that some very delicate and non-trivial inequality holds for all locally Lipschitz functions. So there's that mismatch. So here, the whole analysis I'm making here, the whole argument I'm making is based on practicalities of how you would start building a theory in a natural way, rather than knowing the end result and starting somewhere, because you know at the end of the day everything will hold, right? At the end of the day, this p-Poincare will hold for all Sobolev functions, therefore for all Lipschitz functions, because they are in the Sobolev class. So let's just start somewhere. So far we have seen that assuming up front for all Sobolev is just too much to expect. Assuming for Lipschitz is a bit better. At least we now don't have to talk about Sobolev derivative at this point. But then if we go further down, we then say, how about or require this star for all C infinity functions on B. And here we have the same issue that u of b may not be well defined, so we add this adjective bounded. Okay, so here pros are that gradient u understood in a most classical sense, right? C infinity functions, ub well defined because you're looking at a bounded continuous function on a ball, and ball has finite measure. And then just both sides make sense in the classical sense. And the other pros is here, and this is my reasoning that why this should be the starting point, is that this will imply p-Poincare inequality for all Sobolev functions inside B. Conclusion is that we should define p-Poincare. We say mu satisfies a p-Poincare if, well, these assumptions just to make for technicalities, and there exists this C positive such that the inequality u minus ub d mu less than C diameter B, and then integral average of gradient to the power p d mu to the power 1 over p over ball holds for all balls and all bounded C infinity B b functions. So bounded u in C infinity b. And there's still much more to talk about this, because, for instance, why not assume C infinity Rn, or C infinity compactly supported, or something like that? And indeed, I have been grappling with this question, whether you can even remove this bounded here. If you are not bounded, then we don't know if integral of u is finite over the ball. And I tried to find a counterexample. I have been thinking this whole afternoon on this with various attempts, but I haven't really been able to settle this. So question is, does p-Poincare inequality in this above sense imply that this star holds for all u in C infinity b without the boundedness assumption? That means, of course, if this side is ever infinity, we're good. So it's a very nice question. The resources from which I have seen versions of p-Poincare always assume some boundedness, even when they talk about, even when their definition is with locally Lipschitz functions, they go with bounded locally Lipschitz. So there should be something there why so many authors don't drop it just outright. Now I want to show you a bit of the proof of how I start with assuming p-Poincare for bounded C infinity to p-Poincare for Sobolev, HP of B. Okay, so I'll just sketch it, but it's a nice, cool proof, so I wanted to share it. Okay, the idea is that suppose first that I actually have a C infinity function, but it's not bounded. However, it is in the Sobolev space B. So if I am to prove that p-Poincare holds for all H1b, in particular, I have to prove for the nicer subclass of C infinity n in H1p. So this means, remember, that u is in LP of the ball, and a gradient of u is also in LP of all the ball. But again, this may allow you to be unbounded. So the way you do it, step one, is you first prove that, so for sigma between 0 and 1, let sigma b be dilation of the ball. So it's the ball with same center but radius sigma times. So you first prove that, well, u restricted to sigma b has an average, and you prove that this converges to average of u over b, which is defined because u is in LP and therefore in L1 by Holder, as sigma goes to 1. So once you check this step, it's simply you look at u times characteristic function of sigma b, and this pointwise converges to u, and then the convergence is these functions are all uniformly bounded in LP, so by monotone convergence this function converges in LP to u, and therefore also in L1, therefore integral converges, and then integral average converges, and we end up with this. Once you have this piece of information, by similar argument, you prove that u minus u sigma b as an integral over ball converges, sigma b converges to u minus u of b over all of B, as again sigma goes to 1. Very similar argument. And again, you can just put average here because it's the same constant on both sides basically. And what happens here is that you realize that U restricted to sigma B is now, very importantly, bounded and in C infinity of sigma B. So by definition of p-Poincare inequality, because now you have boundedness, you have that integral average of U over sigma B, U sigma B d mu is bounded by C, diameter of sigma B, which is less than diameter of B, and then integral average of gradient U to the power P integrated 1 over P sigma B. So this is true for every sigma. And what you do, then now you take limit and apply cases 1 and 2. The right hand side, because gradient U is in LP, the right hand side converges to the full integral over all of B. Diameter B is independent of sigma. And then the left hand side, by part 1 and 2, converges to the desired thing. So if sigma goes to 1, we get that Poincare inequality holds for the function U. UP d mu is less than C, diameter B, integral average over B. So we got rid of all the sigma mentions. So because Poincare inequality holds for sigma B's, we deduce this. So star holds for all U in C infinity of B, intersection H1P of B. So we have succeeded in proving Poincare inequality for a subset of this. The fourth observation is that both sides of the p-Poincare inequality are continuous in the Sobolev norm. Then it holds for closure, and with the same constants, for the closure of C infinity B intersection with H1P of B. But this closure is just H1P and B. And that ends the proof. So the parts that I didn't include were really just measure theory, pointwise convergence, monotone convergence, and stuff. And this proof shows how assuming p-Poincare inequality for bounded C infinity functions easily gives us p-Poincare inequality for the Sobolev space defined through closure of C infinity functions. So I believe that the definition through bounded C infinity functions is very natural without requiring some a priori knowledge, and at the same time it's strong enough to imply the version for all Sobolev functions. So if you find the answer to this question about whether we can remove bounded from that assumption, I will very much be glad to see that solution. Okay, I expect to see more from weighted Euclidean spaces from me, as I have been having some fun with them and I want to share more of their story.